Good morning, students. In the last class, we discussed about relationship between conductivity and molar conductivity, as well as we have calculated conductivity, and also we have determined the determination which one, that cell constant, by the use of KCl. Okay. So today we will start one more concept, that one is a variation of conductivity, that is, and as well as molar conductivity with a concentration. So first one is a variation of conductivity, variation of conductivity with concentration, variation of conductivity to concentration. So later we can study for that molar conductivity. So conductivity is or specific conductivity or specific conductance or specific conductance refers to conductance of 1 cm cube of electrolyte, conductance of 1 cm cube of the electrolyte. So with increase in dilution, the number of ions in 1 cm cube decreases. So therefore the conductivity decreases. Therefore conductivity decreases as the dilution increases. Okay. What is that one? A variation of conductivity with a concentration. Already you know that the conductivity as well as specific conductance, it depends upon that is 1 cm cube of the solution or 1 cm of the electrolyte that is present in the system. So with the increase in dilution, what happens? The number of ions present in 1 cm cube decreases. So therefore the molecules are move apart. Because of this one, conductivity decreases as the dilution increases. Next is a variation of molar conductivity, variation with the concentration. Variation of conductivity, that is molar conductivity with the concentration. So already as per the relation, so that is lambda as per the mathematical equation, so that is lambda m is equal to 1000 into that is specific conductance divided by C. Means as C increases, lambda m decreases, or as C decreases, lambda m increases. So usually a lambda m for strong electrolytes, is always greater than lambda m for weak electrolytes. Okay. So lambda m for strong electrolyte is always greater than the lambda m for weak electrolytes. So in case of strong electrolytes, like KCl and ACl, in case of strong electrolyte like KCl, the concentration approaches to zero. The molar conductivity attains a definite value molar conductivity attains a definite value and definite value and definite value that is known as that is known as limiting molar conductance, limiting molar conductivity, limiting molar conductivity, limiting molar conductivity. So that is denoted by lambda m naught. Okay, this is denoted by lambda m naught. So this lambda m can be determined, that is lambda m naught can be obtained by plotting lambda m versus root c graph by extrapolating to zero concentration. Okay, so for example, so that is nothing but this is the graph. So this is lambda m versus c, root c. Okay, so this is for whatever this is taken, this is for a strong electrolyte. So this is nothing but lambda m naught. But in case of weak electrolytes, like acetic acid, the lambda m naught cannot be determined. Lambda m naught cannot be determined by extrapolating. To zero concentration. By extrapolating to zero concentration. By extrapolating to zero concentration, because the graph is parallel to y-axis. So nothing but, so this is for weak electrolytes, this is for acetic acid. Okay, so lambda m naught, that is for zero concentration, lambda n can be determined, and this one is called as limiting molar conductivity. It is applicable only for strong electrolyte. But if you go for a weak electrolyte like acetic acid, it cannot be determined that is lambda m naught, that is zero concentration value of lambda m cannot be determined by extrapolating to zero constant, because this graph is parallel to y-axis. So later we can see the why it can be determined for strong electrolyte, why it cannot be determined by weak electrolytes. So already you know that in case of strong electrolytes, like if you go for KCl, what happens? It is a strong electrolyte, it will ionize completely, A plus and Cl minus. Okay, it is for strong electrolyte. So it will ionize completely. Okay, so therefore the lambda m values are generally high for this one. Is generally high because of complete ionization. Are generally high. Okay? So, however, but in case of concentrated solutions, the density of ions are quite high. The density of ions are quite high, and hence there is an existence of existence of interionic interactions, interionic interactions, interionic interactions, interionic interactions. So because of this, what happens? There is, because of this one, because of this, there is because of this there is a decrease in speed of ions. There is a decrease in speed of ions. Thus the lambda m value decreases. Lambda m value for concentrated solutions decreases. But as dilution increases, the molecules are, or there is, as the dilution increases, there is decrease in interionic interaction. There is a decrease in interionic interactions, and decrease in interionic interactions. Hence speed of ion increases. Thus speed of ion increases. Thus lambda m value increases. For diluted solutions. Right? So means in case of a strong electrolyte, what happens? The lambda m value is relatively high, because of it undergo complete ionization like this. But in case of a concentrated solution, what happens? The density of a particular ions like K plus as well as Cl minus are quite high whenever the more amount of particular electrolyte that is present in a solvent. So because of that one, what happens? There is an existence of an interionic interaction between these two ions. Means because of this one, what happens? The speed of ion decreases. Therefore, the lambda m value for concentrated solution is very low in this case, due to the lower speed of ions. But as dilution increases, what happens? The molecules are move apart. Because of this one, what happens? The interionic interaction decreases, and hence a speed of ion increases. Therefore lambda m value increases for a diluted solution. The mathematical relations for strong electrolyte is given by the mathematical relation for strong electrolytes was given by Debye, Huckel and Onsager, and gave a mathematical equation, so that is nothing but lambda m is equal to lambda m naught minus a root c. Okay, so lambda m is nothing but molar conductivity. It is lambda m naught is nothing but that is limiting molar conductivity. A is the constant. This depends upon viscosity as well as density of ions or the speed of ions, and this one is a concentration. Okay, if you plot this graph, lambda m versus, that is lambda m versus root c. Okay, so we will get a graph like this. This is lambda m naught, that is limiting molar conductivity, and this slope is nothing but minus a. In this case, it is applicable for only for a strong electrode. It is for strong electrolytes. It is for strong electrolytes. So why next we will go for the weak electrolytes now. So already in case of weak electrolytes, already you know this one, like stick acid. Like stick acid is a weak electrolyte. So it undergo partial dissociation, CS3CO minus H plus. Okay, it undergo, that is, therefore the lambda m values for this type, lambda m values are generally low. Lambda m values are generally low because of weak ionization or partial ionization. But as dilution increases, what happens? As dilution increases, the degree of ionization, the degree of ionization increases. The degree of ionization increases. Hence, lambda m values goes on increases. Thus, lambda m values increases. Lambda m values goes on increases. So therefore, when the concentration, but in case of weak electrode, when the concentration approaches to 0, when that C approaches to 0, the degree of ionization approaches to unity. The degree of ionization approaches. The degree of ionization approaches unit value. So that is the electrolyte almost undergo complete ionization. Okay, so therefore the lambda m naught values, that is limiting molar conductivity for weak electrolyte, cannot be determined because it approaches unit value, as well as it is nothing but it undergo complete ionization. But in case of a strong electrolyte, what happens? There should be two types. One is concentrated solution, second one is that is diluted. So in case of a concentrated solutions, there is interaction between its that is interionic interactions are very high. So because of that one, what happens? The speed of ions decreases, therefore lambda m value decreases. But as the dilution increases, okay, the interionic interaction between the ions decreases, therefore speed of ions increases because of lambda m values are very high. So therefore, in order to determine that one, so the mathematical equation was developed, and that one is known as Debye-Hackel, or that is Onsager equation. That is nothing but lambda m is equal to lambda m naught minus a root c. Okay, if you plot a graph of lambda m versus root c, so you will get this type of a graph. So here, this is based on, that is Debye-Hackel Onsager equation. So the which one whenever this curve approaches to this y-axis, that is nothing but zero concentration. This one is a limiting molar conductivity, and this slope will be used as the minus a, and this a is a constant. It depends upon the viscosity as density of ions that is present in the system, and it is applicable only for a strong electron. But if we go for weak electrolyte, what happens? They ionize partially, okay. So therefore the lambda values are very low in this case. But as dilution increases, what happens? The degree of ionization increases, therefore lambda values goes on increases. But when a concentration approaches to zero, the degree of ionization, usually it is called denoted by alpha, it is approaches to unit value. So because of this one, this indicates that the electrolyte almost undergo complete ionization.